In this video, we will learn how aluminum is extracted from its ore through the process of electrolysis. Why do we extract aluminum? Why is it so important? Aluminum, also known as aluminium, has many useful applications, both in industry and our daily lives. And so it is an economically important metal. It is lightweight, strong, and flexible. And although an oxide layer forms on its surface after some time when aluminum is exposed to air, this protective layer keeps the metal strong and intact, and the metal underneath is prevented from corroding further. Where do we get pure aluminum from? Aluminum, the most abundant metal in the Earth's crust, must be extracted from an aluminum ore. Ores are solid materials such as rocks, which occur naturally and which contain valuable metals or minerals that can be extracted. Millions of tons of aluminum are produced each year worldwide from its ores. The most common aluminum ore is bauxite. Bauxite is a red-brown sedimentary rock, composed primarily of aluminum oxide, Al2O3, commonly called alumina, as well as silicon dioxide, SiO2, or silica, the main component of sand, some iron oxide impurities, the most notable one being iron 3 oxide, Fe2O3, which gives this ore its distinctive red-brown color, and small amounts of white titanium dioxide, TiO2. The extraction of aluminum and its separation from other compounds in its ores occurs at large smelting plants. Bauxite is first converted to alumina in the Bayer process, and then alumina is converted to aluminum metal by the Hall-Héroult process. In the Bayer process, bauxite ore is first crushed, ground, and blended. Then it is added to a hot solution of sodium hydroxide. The sodium hydroxide reacts with the aluminum oxide in the ore, dissolving the aluminum compounds. Insoluble impurities are then removed. The dissolved aluminum compounds are then cooled and precipitated, and then heated again to produce alumina. We've just had a brief look at the Bayer process. The focus of this video is really the Hall-Héroult process. The conversion of alumina to aluminum metal is performed using electrolysis. Electrolysis is a chemical process where electricity is passed through an electrolyte, causing it to decompose into its constituent elements. A lot of power is required to drive the electrolysis process, and thus it is costly to produce aluminum. Why then is this method of electrolysis used to extract aluminum? To answer this question, we need to know that the metal extraction method chosen for a particular metal depends on the reactivity of that metal. This reactivity series shows some relatively reactive metals and some less reactive metals placed in order of decreasing reactivity relative to the reactivity of the non-metal carbon. The reactive metals, which include aluminum, have very stable oxides. For example, aluminum does not occur as a pure metal in the Earth's crust, but rather as aluminum compounds. Aluminum oxide or alumina is a very stable compound. It takes a lot of energy to separate the metals from oxygen. In other words, to reduce alumina to the pure metal and to produce oxygen takes a lot of energy. For this reason, electrolysis is the method of choice to separate reactive metals from their oxides. Less reactive metals, however, have less stable oxides. An example of this is iron 3 oxide, which is found in hematite. Less energy is required to separate this metal from the oxygen. Typically, iron metal, for example, is extracted by reduction with carbon, since carbon is more reactive. Carbon will react with oxygen to form carbon dioxide, for example, and this happens in a blast furnace. So metals lower on the list are generally reduced with carbon to get the pure metal. Now we know why aluminum is extracted from its ore by electrolysis. Let's have a look at this process in more depth. We said that alumina is extracted from its ore by the Bayer process, and that aluminum is extracted from alumina through electrolysis by the Hall-Héroult process. This step is what we will look at now. The diagram shows a cross-section of the Hall-Héroult electrolytic cell. It consists of an outer layer of heat-resistant bricks, then a steel shell. The third layer is a carbon cathode lining the cell. The carbon is either in the form of graphite or anthracite. The cathode in an electrolytic cell is the negative electrode. The anodes, which are positively charged, are also made of carbon. The starting substance in the electrolysis process is alumina. Now, usually in electrolysis, the starting compound is melted and then electricity is passed through it to separate its elements. However, alumina's melting point is over 2000 degrees Celsius. So instead, alumina and cryolite are mixed together, and the mixture melts at about 900 degrees Celsius. Cryolite has a lower melting point than alumina and acts as a solvent to create an electrolyte of molten cryolite and alumina. Less energy is used, and production costs decrease. Let's remind ourselves what an electrolyte is. An electrolyte is a substance with freely moving ions which can conduct electricity. Now we know the setup of the cell. How is aluminum generated? First, electricity is passed through the electrolyte using the anodes and cathode. At the cathode, Al3+ ions gain electrons and are reduced. We can write this half equation as follows. Positive ions gain electrons. This is a reduction process. The acronym OILRIG will help us remember this. Reduction is the gain of electrons. The liquid aluminum sinks to the bottom of the cell and is run off and collected through an outlet. The aluminum is then cast into blocks. Negatively charged oxide ions from the alumina move towards the anodes, and the reaction which occurs is shown by this half equation. This is an oxidation process. Oxidation is the loss of electrons, and we can see that these 4 electrons are being removed from the oxygen. In the process, oxygen gas is produced which bubbles off. Some of the oxygen reacts with the carbon at the anodes under these very high temperatures, and so fairly regularly the anodes need to be replaced as they begin to disintegrate. We can add these two half equations to get the overall electrolytic cell reaction. We can rewrite the two equations. Next, we multiply each equation by a suitable number so that the electrons can cancel out. If we multiply the top equation by 4 and the bottom by 3, we get the following. 12 electrons on the left and 12 electrons on the right can cancel out. Now we can add the equations together, and we get the following overall equation. 4Al3+ liquid plus 6O2 minus liquid, giving 4Al liquid plus 3O2 gas. These ions we can combine to the original starting alumina formula. We can see that for every 2 moles of alumina added to the cell, 4 moles of aluminum are produced. Multiple electrolytic cells just like this, sometimes over 300, are needed to produce aluminum at an economically viable rate in industry. Electric current of over 150,000 amperes and approximately 4 volts per cell are needed. This is a highly energy-intensive process, requiring up to about 15 kilowatt hours per kilogram of aluminum produced, which is about 54 megajoules of energy needed for 1 kilogram of aluminum. Scientists are, however, investigating ways to make this process more efficient. Now it's time to practice. Which of the following is not a reason why cryolite is part of a molten electrolyte in the extraction of aluminum? A. Cryolite increases the amount of electricity used. B. Cryolite reduces the temperature at which the aluminum melts. C. Cryolite increases the conductivity of the electrolyte. D. Cryolite provides sodium ions which help to carry the electric current. Or E. Cryolite reduces the working temperature of the electrolytic cell. The extraction of aluminum is a two-step process. First, alumina is extracted from bauxite ore in the Bayer process. Then pure aluminum metal is extracted from alumina in the Hall-Héroult process. This is an electrolytic process. Electrolysis is a chemical process where electricity is passed through an electrolyte, causing it to decompose into its constituent elements. The question asks us about a molten electrolyte. So we know we are looking at the electrolysis process. In the Hall-Héroult electrolytic cell we have a carbon cathode and a carbon anode. Electricity is passed through an electrolyte containing aluminum ions, which gain electrons from the cathode, are reduced to aluminum metal, and this liquid aluminum metal sinks to the bottom of the cell and can be collected through an outlet where it is then cast into blocks. If the electrolyte was only composed of molten alumina, in other words liquid aluminum oxide, then solid alumina would need to be heated to its melting point, which is over 2000 degrees Celsius. This requires a lot of energy. So instead, cryolite, which is a sodium aluminum fluoride compound, is mixed with a solid alumina. Cryolite has a lower melting point than aluminum oxide and acts as a solvent to create an electrolyte mixture of molten cryolite and alumina. This mixture melts at about 900 degrees Celsius instead of over 2000 degrees Celsius, as in the case of pure alumina. Less energy, or less electricity, is therefore used. This decreases production costs. The question asked which of the following is not a reason why cryolite is used. Option A, cryolite increases the amount of electricity used, is not a reason why cryolite is used. Cryolite is used to decrease the amount of electricity needed. The remaining four answer options are reasons why cryolite is added. Cryolite does reduce the temperature at which the aluminum melts. It does increase the conductivity of the electrolyte. It does provide sodium ions that help to carry the electric current, and it does reduce the working temperature of the electrolytic cell. Finally, which of the following is not a reason why cryolite is part of a molten electrolyte in the extraction of aluminum? The answer is cryolite increases the amount of electricity used. Here are the key points we have learnt about aluminum extraction. Aluminum is economically important and has many useful applications. Bauxite is the most common aluminum ore. Electrolysis must be used to extract aluminum from its ore, since aluminum is more reactive than carbon. Cryolite is used to decrease the temperature at which aluminum melts, and this in turn saves energy and decreases production costs. And finally, Al3+ ions in molten alumina are reduced to aluminum metal by gaining electrons.